section 5.4, equilateral and isosceles triangles, you guys. First thing I want you to do is come over to the right-hand side of your notes area, and let's do our best to draw an isosceles triangle, which means that you want the impression that two sides are the same. And then we're going to put some notation markings on this to show that it's isosceles. So what we're going to do to show that it's isosceles, what we've learned in our last chapter, and I know there was some discussion even about, like, we've done this before, your notes need to be out now. If you know, then do it. Then we've got an isosceles. These two sides are going to be exactly the same. And actually, those guys are called the legs. The legs are the two congruent sides. Two congruent sides of an isosceles triangle. They're considered the legs. The two congruent sides of an isosceles triangle. Now, the vertex angle is the angle formed by the two legs. The vertex angle is the angle formed by the two legs. The angle formed by the two legs. So I'm going to go into this drawing and I'm going to label these things on here. That's the vertex angle. This is also a leg. Label your vertex angle and your two legs on there. This third side, you guys, is called the base. Base is the third side of an isosceles. It's not the legs. The third side of an isosceles triangle. And the base angles are where the legs meet the base. The two angles formed where the legs meet the base. The two angles formed where the legs meet the base. These guys are going to be our base angles. And in an isosceles triangle, what we're going to find out is they're congruent. Those two guys are my base angles. Now the one thing, ooh, we got a quiz next door after a day off. That's pretty fierce. Those guys are my base angles. And the one thing I want you guys to think about is these base angles, it makes sense that they're the same length because across from the base angles are these legs. And the angle opens up as wide as the leg is. And since the legs are the same, you got to think about how this angle opens up exactly the same width. Those two are going to be the same. Now, Theorem 5.6 right below this talks about that. If two sides of a triangle are congruent, then the angles opposite them are congruent. So if we know that a triangle has two sides congruent, we can make the assumption that the angles are congruent. If this is known, then, and I'm going to grab a different color, then we can assume what I just put in green. If this is known, then we can assume base angles are congruent. Now, Theorem 5.7 is the converse of that. It says the exact same thing, but in the other direction. If this piece is known, so now I'm going to go back to my known color. If you know that the base angles are congruent, then the assumption we can make then is that the sides are congruent. And so you choose which theorem justifies based on what you start out knowing. Do you know side lengths congruent first and make the assumption about base angles, or do you know base angles are congruent first and you can make the assumption about side lengths? When you're ready to go on, you can turn the page. I'm going to walk around and pass out some tracing paper that we'll use in a couple minutes for a few problems. Take a look at the next theorem if you turn to the next page. Okay, now, when we get to the next page, we're looking at equilateral triangles and a corollary to the base angles theorem. So a corollary follows a theorem. Corollary 5.2, if a triangle is equilateral, all same sides, then it's equiangular. All the angles are the same. Equilateral means all same sides. If that is what we know, we can assume that all the angles are the same. And again, let's go with, if this is what is known, I'm marking in red. If that's what's known, this can be assumed. Page 253. And then the converse of it goes back and says the exact same thing in the other direction. If it is known that we have all the angles the same, then it is assumed that the sides are the same. Known that all the angles are the same, assume the sides are the same. What are the angles of a equilateral triangle? 60, yeah. If all triangles have 180 and these angles are all the same, the measure of each angle in an equilateral triangle is going to be 60. Look what I just did there. Split it up. 60 the measure of each angle in an equilateral, equiangular triangle. 60 is the measure of each angle in an equilateral, also known as equiangular triangle. If the sides are the same, the angles are the same. I'm going to go down to the extra practice, and I gave you guys the small piece of patty paper. And we're going to use this because this drawing, you can tell in this drawing that there's a bunch of different triangles, and they're looking at a whole bunch of different parts of the triangles. So I want to use the patty paper just to trace over what it is that each problem is giving us so we can make some decisions about what we can assume. So this is, we're going to get a known, and then we need to figure out what it is that we can assume. And so the first one in number 1, I'm going to lay my patty paper over, just the corner of it. NJ, let me find NJ. NJ is right here. There's N, there's J. NJ is congruent to NM. All right, so they're focusing on these two sides. Now, I actually maybe even gonna do this. Let me turn it over. You guys see the base is JM? If I turn my paper over, you can see that its base is this JM. What two angles are gonna be congruent to each other? Which angle is across from this JN side? What angle is across from this JN side? The vertex across from it. Just the M is what's across from it here. JK. JN is formed by this opening at angle M. JN is formed by how angle N opens up. How is MN formed? Which angle opens up to make MN? This one. Opens up here. If we know those two sides are the same, it's that base angles theorem. If those two sides are the same, then the angles that are the base angles, that J and M, are the same. That was, go back and find the theorem. Look back. Given is side lengths, base angles. Given side lengths in an isosceles, base angles are the same. Is it? Given the sides, base angles are the same. Is it 5.2, you guys?
Yeah.
Okay. 5.2. Known. 5.2? Yeah, no. Not at all. If two sides of a triangle are congruent, then their angles opposite are congruent. This is what it was. This is 5.6, the base angles theorem. Now I'm thinking that maybe in number 2, we might be looking at the same thing, but we've got to figure out and use our patty paper to mark what triangle we're talking about now. So get to your patty paper and a little clean spot on your patty paper, and they want us to mark LN, LM. Okay, so LN is here. LM is here. So this is the triangle they want us to talk about now. Triangle LNM, and they're giving me the pair of congruent sides. So this one's like number 1. What are the angles that are opposite these sides that open up to the same measure? What side is the base? NM is going to be the base, and when I turned it this way, you can see that a little bit better. So what are the names of the base angles? N and M, there you go. Those sides would be opening up to these congruent angles, N and M. Now I copied it upside down, so it's looking, oh wait, no, it was this way. M and N. Base angles are M, N. You guys might notice something here. Look, in number 1, the two letters that were the same were N. The angles were the other letters. In number 2, L's were the same. The angles were the other letters. It's kind of helpful. M and J for number 1. Now in number 3, oh wait, so this is no different than the theorem we used on the one before. Given the sides, the base angles are congruent. Given the sides, the base angles are congruent. Now I'm reasonably certain that this is going to be, I think it's 5.7, the converse of the base angles. Converse, meaning that we're given the angles are congruent. What sides does that assume are congruent? So we'll have to go into our drawing and see. I'm going to double check. Is it the base angle? 5.7. Yep. Given congruent angles, then we've got sides. So let's go see what angles they're talking about in number 3. Take your patty paper and let's go find the angles they're talking about. They're talking about N, K, M. N to K, N, K, M. That angle is congruent to NMK. Boom, there we go. All right, so they're starting out by giving us this. I'm going to turn mine in just a second because I want you guys to realize that my base then is, boom, here. So I'm just flipping it over so I can look at it as the base. NKM, NMK were the angles. So what sides can I assume? These angles open up to what two sides? N to K. M opens up over here, MK, or NK, I'm sorry. Angle K opens up to MN. So this tells me that NK segment NK, side MK, NK is equal to side NM. Same idea for how we're going to, that is definitely the converse of the base angles theorem. When you're given the angles, you can assume the sides. Converse of base angles. And number 4 is going to be the same. Given angles, figure out the sides. Take a minute and trace what they've given us for 4. You should have enough room on your tracing paper. Let's see what we got. LJN, LJN, LNJ. Okay, so now they've got us on this triangle here. They've got us looking at LNJ. This triangle. These two angles are congruent. This is the base. It's actually sitting on its base now. We can make the assumption that those two sides are congruent. Get that notation down on your page for number 4. Those angles, angle J opens up to LN. Angle N opens up to LJ. Turn your page when you're ready to go on. Actually, I'm going to pass around some tape. I just want you guys to take, and all you're going to do, maybe I'm going to pass around tape. Yeah, all you're going to do is just take one piece of tape and put this here so you could like flip it up if you needed to. But just keep it in there because that's where all our work was with this. Just take one piece of tape and tape that into your notes right there so it hangs out and doesn't get missing. Pass that around. That's out there. I'm going to turn the page. And let's take a look at these last practices together. And then you turn your page and make sure you don't mess up your, yeah. So, number 5, you guys, what kind of triangle do we have when all the angles are marked the same? Equilateral, equiangular. How long is X? If L to M is 31, we're talking lengths. If L to M is 31, now do our side lengths have to all add up to something? Because you guys are talking right now, you're talking about this. And that's cool that we know that, but what do we know about all the sides? They're all the same. So what's the value of X then? 31. You got it. X equals 31. This ln would be 31 as well. We could make that assumption. Now in number 6, they're showing us, check it out, it's equilateral because all the sides are 12. If all the sides are 12, what's the measure of all the angles? If all the sides are the same, all the angles are the same.
2x.
So every one of these angles is 60 degrees still. So that means then that 2 times x is 60. What does that make x? Yep. So looking that they're giving me all the side measures are the same, I make the assumption all the angles are the same. And again, there's not going to be, our side lengths are going to vary by the triangle. It's the 60 degrees that'll always stay the same, but the side lengths vary by the triangle. We just know in an equilateral that they're all the same. These are our equilateral, you guys like this? Lateral and angular. All the sides and angles are the same. Our equilateral, equiangular triangle. Now I know 7 and 8 is a little bit different, isn't it? Now in problem 7, I think actually in 7 we're gonna be on the struggle bus a little bit to figure out what x is, because I think we're gonna need some trigonometry. We may not find x, but I'm confident we can find y. Now I'm gonna ask you guys to first focus here on this triangle, because I want you to think about this triangle, because this triangle is isosceles. Oh yeah, we're gonna be able to find out what x is. We absolutely will be able to find out what x is, but we've got to find y first. This guy is isosceles, and I can tell that because the base angles are marked the same. So those two guys are isosceles. Now, I don't know what these base angles are, but this one over here is equilateral. So what do I know about all the measures of the angles in this triangle? These guys are all 60. Now, this little marking over here tells us that the angle in the triangle I shaded around in red and this one add to 90. What's the measure of this angle inside our isosceles? That's going to be 30 because the right angle marking. So let me pull this triangle off now, and I just want to put it over here so we can focus on what we've got. We know the sides are the same, and we know this is 30. And the question is, our y is unknown and it's right there. How can we figure out what these base angles are? This is the one I'm pulling off over here into red. What do the angles of any triangle have to add to?
180.
180. We've got 30 right here. So how many degrees are left to split between these two equal angles? That's got to be 150. So if this is 30, these two angles have to add up to the other 150 degrees, which makes each of them 75. 150 divided by 2 is 75. So that tells me then, based on my drawing, they wanted a y. Y is 75. We got that by looking at the isosceles triangle.
What are we supposed to do with the tape again?
Just tape your little sheet in there.
We already saw x.
No, we're going to get to x right now. How long are all the sides of the equilateral triangle?
60. I was just checking.
How long are all the sides of your equilateral triangle if y is 75? Take a look. They're expressed as y minus 25. We know y is 75.
75 minus 25.
I'll get it in a sec, or you can bring it up.
So each of them is 50.
So yeah, 75 minus 25, each of these sides of this triangle is 50. If y is 75, and I'm sure it is based on what we did, that makes this 75 minus 25. It makes this side 50, this side 50, this side 50. This is side length now. We're going around. Y is 75. This side was expressed as y minus 25. 60 has to do with the angles. All three angles are the same in this because it's equilateral. 180 divided by 3 is 60. What's the value of x? So we said this side was 50 based on, because it's shared. That makes x 50 as well. We've got them both. Makes x 50 as well. Now this next problem, maybe this will make it a little bit easier because we're using things interested in you guys focusing in on. Again, we always take this stuff into high school land and it gets harder. So this guy right here is isosceles. In any isosceles triangle, I can make this assumption. If the sides that Theorem 5.6 tells us, if the sides are the same, the base angles are the same. Now, if one of the vertex angle is 40 in this isosceles, and I'm not thinking about this triangle yet, if the vertex angle is 40, how much is left out of 180 to split between these two? 180 minus 40 is 140. Divide 140 in half. Think cash. 70 each. So x is 70. Now, if x is 70, I can go do this now. This side can be expressed as 70 minus y. Let's focus in on this equilateral triangle now. Anybody have an idea about the equation I could solve to figure out what y is?
2y plus x minus y? No, 70 equals...
How do I relate these two? I know what x was. X was 70, so now I'm rewriting this as 70 minus y.
Yeah,
How can I relate these two quantities? What do these markings mean?
they're the same.
They're the same. So let's set them equal to each other. Set them equal to each other. We know they're the same. I'm going to start this by adding y to both sides. You can start multiple ways, but I want to start by adding y. 3y plus 10 is 70. What's my next move? Let's get 10 out of there on both sides, across the equal sign. 3y is 60. Divide both sides by 3. Y is equal to 20. X is 70. Y is 20. Now I'm going to go back and just check that real quick. Let's see. So 70 minus 20 is 50. That works. 2 times 20 is 40 plus 10. That's 50 as well. So they work in both.